Okay, starting video 5 now, we can look at the architecture of neural-machine translation. So, you know, again, we're going from source language to target language via machine learning of some type, typically deep learning these days, English to German perhaps, as we've got here. And this is essentially a comparison of phrase-based statistical machine translation with neural MT. And this one slide, an important slide, signifies the main reason why neural machine translation works better than SMT. So in SMT, you'll be well used by now to the fact that we take an input sentence and we split it up into words and phrases. And we only ever translate words and phrases individually into target language words and phrases. And then we try to combine those with the target language model to produce what we hope will be a good output sentence. In neural MT, we have available to us the hidden state of the network at the very end of processing the whole source string. So we have the context, the history of what the neural network did in order to process the whole string. And this hidden state is what is input into the decoder. So we're now at the point where we can actually go through the encoder-decoder architecture. So we have a string, the cat on the mat, that we're going to process one word at a time, as we've seen already, using the time unfolded neural net as a representation of what the state of the network was when it was processing particular words in the input string. So we do one word at a time. The network, changes as it's updated as we process different strings, different words in the string, and we do that word by word, and we end up with, as I say, the final state of the encoding process representing the whole sentence. This is fed into the target side, okay, where we start to now use language modeling to try to predict the best Italian sentence here. So, given the start of the sentence indicator, we have to try to predict what the most appropriate output word would be in the target language. So here we just predict the word with the highest value, which happens to be il, the masculine singular determiner equivalent to the in Italian. We can then predict the next word, gatto, and then continue on through all of the words until we have output a single output string, which is perhaps the best translation that the neural net can come up with. But all of this, the whole translation was generated from the final encoder state. An improvement to that encoder-decoder model was to add in a third neural net. So the encoder is a neural net by itself, the decoder is a neural net by itself, but we have this attention model, which is essentially akin to the alignment process in SMT. And essentially, it enables us, when you're processing a particular word, to look ahead and say, look, this other word provides key information which you ought to take into account in processing this word. So if we have a word, an English word like bank, for example, we don't know whether that's going to be translated into, let's say, French as the bank of the river or a financial institution. But if I can look ahead and find a word like river, then I know that I ought to, in the English string, I know that I ought to translate that as riverbank, not financial institution. If I go ahead, if I look ahead and I find a word like money, then I might translate that as financial institution and not riverbank. So the attention model essentially provides extra clues in the decoding phase as to what other words are important to focus the mind on in order to try to predict the most likely or most appropriate output word at that particular point. So one further improvement was to add bidirectionality. So I've assumed, as we're going through this example, that we've gone from left to right, but we could equally go from right to left, or from left to right and right to left. And in 2015, the bidirectional RNN was introduced. And this, what you see in front of you now, is really the state of the art even nowadays. Even as we've gone to the transformer model, this essentially what you see here, an NMT system, encoder decoder model with an attention model intervening in between the two phases, is essentially the state of the art today. Here's a neural net for handwriting recognition, trying to recognize just 10 different symbols and make a prediction as to whether it should be a 0 or 1 down to a 9, and you can see how complicated this is already. So a neural net for translation or image recognition or speech recognition is going to be very, very complex indeed.